Okay, in this video I'm going to talk a little bit about the Linux file system and talk about how it's organized. Um, so the Linux file system we know exists on some sort of storage device, some storage medium. We know that the computer has some sort of way of translating some physical properties of storage into ones and zeros, right? For example, a hard disk drive, some of the older platter disks use magnetic platters, and the orientation of the magnetic data that is stored on that disk can be interpreted as ones and zeros. So there are lots of different storage media types, and they all store data in different physical ways, but that can all be translated by the computer eventually to zeros and ones, right? So we have this big field of data on whatever storage device we're talking about. So the Linux file system attempts to organize this big blob of ones and zeros, right? So how does it do this? Well, there's something that's called a superblock. That's one section of this big blob of ones and datas, of the field, if you will, a field of data. And then there's another partition or field of data that is the inode table, and then a third area that is data blocks, and actual data is stored. Okay, so the superblock is critical, and it basically defines how the rest of the device is chopped up and organized, right? So it defines how many inodes there are in this inode table, and it defines how big every single one of these data blocks is, right? So data blocks are just big chunks of data, and essentially they're used for storing file data or directory data, right? And so as a file grows in size, it might exceed the size of one of its data blocks, right? So it's up to the file system to say, okay, we need one more data block for this file, and it will allocate another data block. But it has to keep track of where these data blocks are, because there might already be something stored here, and so it will have to skip over and store the data elsewhere, right? So that's what the inodes do. They keep track of where the data in the file is stored. All right, so this is just kind of a high level. We're going to go more into depth about this, but just keep in mind that the superblock is the definitions of the file system. It's critical to the file system, and it's backed up in lots of different places on the hard disk, because if this gets corrupted, you won't be able to access anything in your file system. All right. So what is an inode? So we got this idea of an inode table. It's a block of data on the storage device that is used by the file system to store and keep track of the inodes. Okay, each inode has a number, which is like its address. So the inode table associates inode numbers with the inode data itself. Okay, so this is just a table, inode 0, and here's the inode data. Inode 1, inode data. So it's just a table. What is an inode, though? So it's one of a collection of the items in the inode table, right? And it contains information about size, access, modifications, permissions of files and directories, right? It most importantly keeps track of the addresses of the data blocks that are used to construct the file system object. So there's always one inode per file system object. So every file has one inode. Every directory has one inode. A link has one inode. Okay, so remember that the inode has a number, and then all of the extra information about the file. So previously we've talked about the contents of a file. We use the hex dump command. I've got a little file here. If we type ls, we have a file here called hello. And we see the cat command translates the binary data into characters using ASCII, right? And it prints out those characters. But this is all just stored as binary data. And we can use the hex dump command to look at this file data. And we see this is the hexadecimal version of that binary data. So these 2 bits of hex would be 8 binary digits, 8 bits, or a byte. So every 2 hex digits is a byte. And every byte can be represented as an ASCII character. All right. So as we increase the number of bytes, eventually we're going to exceed the size of one of our data blocks, at which point we need to include another data block, right? But within this data, nowhere does it talk about where this data is stored, where's the address of the data blocks this is stored. This is just the raw data of the file itself. So all that information is stored on what's called an inode. And if I use this special command status, it looks at the status of one of my files. So the stat command gives us more information. It looks at this file, and it looks within the inode. All of this stuff is stored in the inode. The size of the file, the number of blocks, right? And here we have permissions, right? So this is 644. This is the user can read, write, and no execution. The group can read and write with no execution, and everyone else can just read it, right? User ID, access time, when was the last time this was accessed? When was the last time this was modified? And when was the last time this was changed? So this can be a little bit confusing. The modify time is when the file data itself changes, right? So that's the information on the data blocks. And the change time is when the actual metadata, so the information in the inode about the data, so metadata, whenever that's changed, right? So all this information is stored in the inode itself, and it even gives us the inode number, right? So in our inode table here, this is a list of inode numbers and then the actual inode data. So all of this would be inode data, right? All this stuff. And notice we have the file name in our inode data, right? So when we look at the data itself using hexdump, we see this is the contents of our file, but nowhere do we see the file name or the size or the permissions or any of that stuff. That's not actually part of the file data, right? That's metadata about the file, and that's stored in what's called an inode. And the inode has a number, and there's one inode per file system object. Okay, so this is kind of how the Linux file system is organized. All right, so moving on to a data block, we've already kind of covered that, but it's essentially just a fixed size. It's a block of ones and zeros, right? And that's defined, how big these data blocks are is defined in the superblock. It's defined by the file system, right? So how big are these blocks? That's up to the file system. But as files or file system objects grow, right, you're going to potentially need more and more blocks. And so the inode has to keep track of where this information is stored and the order that it's stored in, right? So the data blocks do not have to be contiguous. They don't have to be one right after the other. It's convenient when they are, but they don't have to be. They can be anywhere on the hard disk. It just, if they're not contiguous, then it might take a little bit longer to retrieve, but the system is so fast, it's hard for us to notice these days. All right. So expanding on this this initial image up here, right? We've got some chunk that's the superblock. That these are the core definitions of our file system. We have this idea of an inode table here in orange, and this is just a list of inode numbers and the metadata about files or file system objects, right? And then data blocks. Okay, so those are the three primary sections. So those colors still correspond in this particular image. So within the superblock, it's defines this idea of the root directory entry. So a dentry is a directory entry, and that's basically just a name and an associated inode. Okay, so that's dentry. It stands for directory entry, and it's a mapping of a file name to an inode. So when you have a directory, when I'm over here on the command line and I use the ls command, this is actually just looking at the directory's data block, and because it's a directory, it's just a mapping between file names and inodes. So when I use the ls command, it's just printing out all the names, right? And there's an associated inode for each one of these. I can look at that inode using ls-i. And so this is essentially all the directory data blocks store. They store a name and then an inode. It's a table. We have a name and an inode associated with that name. A name and an inode. Right? We've got three entries in our data block here for this directory. And again, this is the information that's stored in the data block. Right? It's names and inodes. Right? For a directory. So everything in Linux is treated the same way. Everything is considered a file. Right? So file data is just the data in the blue blocks here, right? So when I look at, hex dump -c hello, right? This is information that's in the data block in that blue area, right? Just like when I type ls, this is the information that's stored in the data block. ls-i shows all of it, right? Now there's a special format that it's stored in, right? Because it's a directory, all the directories store this in an efficient way. So there's a special structure for how this is stored, but essentially it's all still stored in a data block, just like any file data would be stored in a data block. All right, so if we look down here, the superblock defines kind of the root of a file system. We know that ls / is considered the root directory, the root of the file system, right? So if it defines this as inode 0, okay, then we can go up here and we can locate in our inode table what's at inode 0. Okay, grab this inode data. So this block here represents that inode data, right? So you have some metadata about this inode, when was it created, when was it accessed, all that different stuff, the permissions, and we also have some information that says what kind of data are we dealing with, right? We have normal file data, and then we have directory data, and we also have something called link data, which we'll go into a little bit later, right? But the directory data is specified in the inode, and basically it just tells us, oh, if this is directory data, then expect a certain format here in the data blocks. The certain format is inode and name mappings. It's a data table of the names of files and the inodes associated with them, and they could be files or directories, right? Pretty much everything is treated the same way in a Linux system. Everything's a file. You might have heard that before. It's a common phrase. In Linux, everything is treated as a file. Okay, so directories are just files that contain a mapping of names and other inodes, right? So if this is inode 0, this is the root of our file system, right? And it has all that metadata, right? Access times and all that stuff, permissions. But then it has a section that is data blocks. What data blocks are we looking at in memory to retrieve all of the data associated with our root directory? Well, this is a directory, so it's going to be a table of names and inodes, and that's going to be stored in blocks 1 and 4. And this could be a huge list or a small list, right? But for just the sake of this example, I picked a couple of numbers. This is in data block 1 and data block 4, let's say. So we go up and we grab data block 1, and that's the first part of our list, but it's too small to hold the whole list, and so we have to go grab data block 2, and that's over here. And realistically, there might be lots and lots more things in here. As we see, we type ls/ and we have all of these different other files and directories in here, right? So, but for the sake of this example, the data blocks are then looked up, right? We have data block numbers, so we can access them. We pull that information down, and it's a list of names, right? And if I use our ls-i for inode, we can look at the inodes associated with some of these things, right? So 1, sys, is the first one, the first inode, right? And so we do see some duplicates. So what's interesting is sometimes this data can be, these inodes can be duplicated. And you can have a name that is the same for another inode. Right, so that has to do with linking. All right, so if I say ls, let's see, So there are some, especially with the / the root directory, there are some more complicated things going on, and we see that there are different listings in /proc and /sys. But for the most part, what we need to recognize is that there are inode numbers associated with the different directories, and those inodes list out the different data blocks stored on the hard drive. All right, so for a more common example, we'll go back to the desktop and type ls-i, and we'll see what's in here. Here we have these items here. Okay, so hello has the inode 721.0.406. All right. So each one of these is what's called a dentry, or a directory entry, right? And it's just the mapping of the name to the inode. Now, a link is a special file system object that can basically duplicate a reference to an inode. Okay, so this name is part of our path, right? This name is associated with this particular inode. And hello, as we know, if we look at the hex dump command, that is associated with these data blocks, however many data blocks that might be. This is a small file, so it's probably just one. But that's associated with these data blocks stored on the hard drive. If I make a link using the ln command, I want to link my file hello with a file called h2. Right? So if I execute this, I can look at ls-i again, and here we see hello and h2, and they have the exact same inode number. Okay, so what's happening here is both of these items, if I look at ls-l, right, it looks like we have two different files here. I can use ls-li to include the inode number, right? So these are two separate entries in my directory, right? This is my desktop directory. They have two separate names, but they both point to the same inode, right? So what happens if I were to change the permissions here? Let's change this to 700, so only I can look at this. And I want to change the permissions of just the h2 file, right? That's these permissions. So this should change to read, write, and execute, and then nothing for everybody else. Right? So if I do that, ls-li, notice it changed it for this file as well. It's because they both point to the same data, and this information, the same inode, this information is stored in that inode. So if I change that information for this inode, it also changes it for this, because they're the same, right? So these are just two different names for the exact same data. So to confirm that again, let's open the file and with nano, and we'll say you are great. We'll save that. All right, so that was our file hello, and now we can echo h2. I'm sorry, cat h2. Right, so we see it changed the value for both of the files. Well, it didn't really change it for both of the files, is because they are the same file. There aren't two files, there's two file names. Okay, so that's what a link is. It's a file system object that's just an additional name for that file, and you can move this to other directories, right? I could move this into an entirely different part of the directory structure, and it would still point to the same data blocks on the disk, right? So we would have basically two entries here. One would be named hello, and it would point to, you know, this node number, right? And then we have another entry in some other directory, and it would point to the same inode number, right? So that, since there's just one inode, the inodes are what point to the data blocks. So then it would have to point to the same data blocks. Okay, so that's what a link is. And there's also something called a soft link. Okay, so to create a soft link, or is sometimes called a shortcut, I can use the ln command -s, and what do I want to make a link to? I'm going to use my hello file, and then I'm going to make a shortcut. Alright, and we see it shows up on my desktop with that little arrow. So this is similar to Windows. You might have seen that with the little shortcut arrow. So these are the types of links people might be most familiar with as opposed to the hard links. Shortcut, if we look at ls-li, the shortcut is a soft link, and see how directories are labeled with a D here? That's because that inode has a special type. The inode says this is directory data, and that tells us that the data blocks are a list of names and inodes, right, in a special format. So that's what that data type tells us, right? This is another type of data. This is telling us, hey, we have a link here, and this is stored on the inode as well for this link. Notice this inode for this shortcut is not the same as the inode for our links, or our hard links, right? So this is the hello file, and it's associated with this inode, which is the same inode as h2. But this is an entirely different inode, right? These two inodes, this inode, which these are just duplicating the same data because it's the same inode, these are files, right? That's when we see ls-l, it shows the hyphen if it's a file, or a D if it's a directory, or it shows the L if it's a link. And that's just telling us that this data block is formatted in a special way, and that's a link. And this is a soft link. So notice the permissions are everybody has access to everything. Even if I change the permissions, the chmod command knows never change the permissions of this link itself. When I run the chmod command, it'll change the permissions of the associated file. So this inode is a special inode that points to a path, right? So it points to the name, hello. And then whatever's at that name is this inode. And then that inode is what we're talking about, right? So whenever I reference shortcut, so let's cat shortcut. It still reads out the contents of the file, but that's only because shortcut points to a path, and all of these commands know to follow the shortcut, whatever path it points to, that's what we want to interact with. Right? So if I chmod 600, I don't need this file executable because it's just a text file, so I'll make it read and writable for myself, and I want to chmod shortcut. So this is our soft link. ls-li. It didn't change our permissions to the shortcut, but it did change the permissions to what it pointed to. Alright, now it shows up here that this points specifically to hello. Well, what happens if we move this file? I'm going to move hello to hello.txt. ls-li. Oops. Now we see this is in red. Alright? It's because it's still pointing to hello. It's associated with a file name, not an inode. So if I change the file name, I try to cat and see what's inside of this, there's no such file or directory. Okay, so that's how a soft link works. Right? It is a separate inode. It's stored in a different way in the data blocks. It has its own inode and its own data blocks, but it points to another file name. Right? A hard link is a file name. It's just a dentry. It's a new directory entry, which is just a file name and an inode, and it just so happens it has the same inode number as another dentry. All right. So one thing to take away from this is when I move a file, right? If I move hello.txt, right? I did that before. I moved hello to hello.txt. the data blocks, the contents of the file itself in blue here, never changed, right? What did change is the directory entry. So the file data was stored somewhere in these blocks. Now my directory desktop has a data block somewhere that has a bunch of dentries in it. So what I did is I took one of those dentries and changed the name of it, right? Or removed it and added another one that pointed to the same inode, right? But the actual file data never changed. It never moved anywhere on the disk. Same thing if I were to remove a file. If I remove the file H2, that file never leaves the operating system, or never leaves the disk until the system thinks that it needs to use that resource location again, right? So if I remove a file, I'm really just deleting the directory entry, right? The data still remains on disk somewhere in these blocks. Now eventually the system will need that space and it will overwrite it, but it's actually costs a lot in efficiency to overwrite files all the time. When you think about it, a storage medium, if you were to overwrite the data every time you deleted something, it would take a long time. First of all, you'd have to spend all the locations on the disk and change the bits, right? And you'd have to do it a few different times to make sure, that no one could tell what was written there before, right? And not only would it take a whole lot of time, but the disk, as you're deleting these items, it would take a whole lot of time, and I lost my train of thought there. But the point is, as you delete these, it's just the dentry files that go away, right? And if you deleted these, it would take all sorts of time, and the other thing was energy, right? It would take a lot of energy resources, electrical signals. They actually have to move the platter around, right? It would be very energy inefficient, especially when you delete things, and large files in particular, right? Gigabytes and gigabytes of data, video files, that sort of thing. That would take a really, really, really long time to delete all that data and bring it back to zero. So this is why a lot of the times you can use data forensics. You might have heard that term. So when somebody has deleted a file, it's not technically deleted necessarily. It may have been, right? The file system, an operating system, may have decided that they need to reuse some of that allocated space, some of those data blocks, but it may not have been. It may still reside there, right? All you would need to know to reconstruct it is the data blocks and the ordering of those data blocks. So if you could find the link, right, based on the way the data is formatted, for example, if I know how a particular type of data is formatted, I might be able to tell that this block matches that block. It's like a puzzle, right? Where do these two pieces go together? And if I put these two pieces together, does it make sense? Is it the beginning of a picture, right? So it's very much like a puzzle, right? And you have to know the formats of data and all sorts of different things like that. But it's very interesting stuff. But that's where the idea of data forensics comes in. It's because when you move something or you delete something, all you're doing is moving around these dentries, right? The actual data itself remains intact on the disk. Okay, so that's the basic idea of Linux file systems and sort of organizing storage devices, these big blobs of ones and zeros that we're used to thinking about. How does it actually work in terms of moving things around and creating, using some of the Linux commands that we're used to using, like move and remove and copy. Copy is one of those commands that not only does it create, it has to create a new dentry, but it's going to point to a different inode, and it's going to actually have to duplicate the data blocks, right? So the copy command can take a long time depending on the size of the data, because you are actually making new data blocks. Even though those data blocks hold the same information, when you make a copy of the file, those two files are different, right? So if I make a copy of H2 and copy it to H3, right, I can look at nano H3, and add some text and exit out of there. Now we see H3 is different than H2, right? And we can also see that in ls-li, right? So H2 matches hello.txt inode, and H3 is a new inode, which means it has duplicated the data blocks, right? So that's sort of the basics, high-level view of how this works. There are particular formats for all of these things. A particular format for the inode, the superblock, is very complicated, and we saw previously, if you look at ls-if/, there's some unintuitive behavior going on there. So it's far more complicated than all of this, but this is the basic idea, the basic understanding of what's happening. And another important thing to remember here is that directories and files are essentially stored the same way. Everything's a file, right? There's a data block, right? And that the data stored there is just formatted for directories, right? So that's all. That's really the only difference. This inode specifically says it's a directory, which means that data block, however many data blocks you pull down, they're just going to be formatted for directories, right? Whereas file data is kind of arbitrary. It could be anything. It could be a text. It could be a text file. It could be a PNG file. It could be a video file, audio file, whatever, right? So file data is kind of arbitrary, but then directories have directories, and then links are a special format as well. It's a special type of inode. Okay. So hopefully that helps you understand a little bit about how the Linux file system works.